Spatiotemporal tomography, based on scattered multiangular signals, and its application for resolving evolving clouds using moving platforms. Climate and clouds strongly interact. Clouds regulate solar energy reaching the surface and thermal energy radiated back to space. Clouds are also central to the water cycle. Reducing major errors in climate predictions requires better observations and understanding of the 3D structure of clouds. The inner microphysics and structure of clouds can be estimated by scattering tomography, based on high-resolution multi-view images from space. Spaceborne systems are so expensive that it is difficult to deploy them in large numbers, such that the same clouds are simultaneously imaged from many directions. Therefore, in practice, platforms orbit above the clouds. During a couple of minutes of motion, an image sequence spans and samples a wide angular range. During this time, however, the cloud evolves. Hence, there is a clear need to derive scattering CT of clouds in 4D, both spatially and temporally. We assess the temporal autocorrelation function of liquid water content in warm convective clouds. The correlation time is about 25 seconds. To suit this correlation time, a temporal sampling interval of 25 seconds is efficient and leads to a low error of cloud recovery. Consider the cloud liquid water content at time t. Using the estimated cloud liquid water content at time t in a forward physics-based renderer yields synthetic model images. A data feeding cost compares these images to the ground truth image data. Then, the cost function gradient can be calculated. Consider cloud images that were taken at n time steps. We use an iterative procedure for recovering the cloud at these n time steps. Consider the 3D cloud recoveries at the kth optimization iteration for these times. We calculate the cost function gradient in separately per time instance. We define an update vector G, which exploits information from different times and viewing angles. G is a convex linear combination of the cost gradients per voxel. The weights are drawn from a temporal Gaussian. The estimated cloud liquid water content at each instance is updated iteratively using this combination. Simulations show that our solution reduces the retrieve error of the 4D liquid water content relative to a solution that assumed the cloud is static during the imaging process. Best retrieval is obtained when the standard deviation for the Gaussian weights is about 20 seconds, which is similar to the cloud correlation time. We demonstrate our method on real-world data acquired by JPL's AirMSPI with 21 viewing angles. We have no ground truth here, hence, we use cross-validation. We exclude the nadir image from the recovery process. Thus, tomography uses 20 out of 21 raw views. Afterwards, the estimated clouds was used for physics-based rendering of the missed nadir view. The result is then compared to the ground truth missing view. Here, we compare the result of this process for two solutions, our 4D tomographic solution and state-of-the-art 3D static scattering tomography. We derive computed tomography, or CT, of a time-varying volumetric scattering object, using a small number of moving cameras. We focus on passive tomography of dynamic clouds, as clouds have a major effect on Earth's climate. Spatiotemporal CT is achieved using gradient-based optimization, which accounts for the correlation time of the dynamic cloud content.